Physics allows humanity to understand and predict the behavior of the universe with astonishing precision. From the motion of galaxies to the interaction of subatomic particles, physics provides a framework that explains most observable phenomena. However, there are extreme environments where the laws of physics cease to function. These are places or conditions where our current theories break down and the behavior of the universe becomes unpredictable and mysterious. These are the 5 places where the laws of physics do not work as we know them. 1. The Big Bang Singularity. The Big Bang Singularity marks the birth of the universe, occurring roughly 13.8 billion years ago. According to the Big Bang theory, the universe began as an extremely hot, dense point, a singularity. This singularity, where all matter, energy, and space-time were compressed into an infinitely small volume, represents a moment where the laws of physics, particularly general relativity, break down. At the singularity, density and temperature reach infinite values, making it impossible for the equations of general relativity to describe what happens. Quantum mechanics, which governs the behavior of particles at the smallest scales, also struggle to provide a coherent explanation. A unified theory of quantum gravity is needed to describe the very early moments of the universe. But until we have such a theory, the physics of the Big Bang Singularity remains a mystery. 2. Inside black holes. Another place where the laws of physics cease to function is at the heart of a black hole. Black holes are regions of space where gravity is so strong that not even light can escape. At the center of a black hole lies a singularity, much like the one that existed at the beginning of the universe. This is where all the mass of the black hole is compressed into an infinitely dense point. In this singularity, both general relativity and quantum mechanics cannot describe or predict what happens. The gravitational pull becomes infinite, and space-time is stretched to the breaking point. Time and space as we understand them stop behaving normally. Like the Big Bang, the black hole singularity represents a situation where a theory of quantum gravity is needed to provide a clear understanding of what actually happens. 3. At the Planck scale, also known as quantum foam. The Planck scale, named after physicist Max Planck, refers to the smallest possible units of time and space. The easiest way to understand how small a Planck length is would be to measure the diameter of an atom. The diameter of an atom is an astounding 100 million Planck lengths, giving you an idea just how small the Planck scale is. At this scale, space-time itself is thought to become turbulent and chaotic, a state often referred to as quantum foam. At the Planck scale, space-time breaks down and ceases to function due to quantum effects. Instead of being continuous, space-time fluctuates wildly, filled with tiny, short-lived particles and energy. This quantum foam makes it impossible to apply our conventional understanding of physics. General relativity and quantum mechanics cannot describe the behavior of space-time at these incredibly small scales. 4. Extremely high energies, the Planck energy. Another place where physics breaks down is at extremely high energies near the Planck energy. At these energy levels, the distinctions between the 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force all begin to blur. It is theorized that at such high energies, all these forces merge into one unified force, similar to the conditions shortly after the Big Bang. Neither quantum mechanics nor general relativity can fully describe what happens at these energy levels. Quantum field theory, which explains the behavior of particles at lower energies, doesn't account for the gravitational effects at extreme energies. While general relativity, which describes gravity, does not incorporate quantum effects, we cannot accurately predict the behavior of the universe at these extreme energy levels without a unified theory of quantum gravity. 5. The Cosmological Horizon, the edge of the universe. The cosmological horizon represents the edge of our observable universe. Due to the accelerating expansion, objects beyond a certain distance are moving away from us faster than the speed of light, driven by dark energy. This means that light from those objects will never reach us, rendering them unobservable and putting them effectively beyond the reach of our laws of physics. According to the current understanding of general relativity, nothing can travel faster than light. But the expansion of space itself causes objects to move away from each other at speeds that are actually faster than light, challenging our understanding of physics. This raises questions about the nature of dark energy, a mysterious force that constitutes roughly 70% of all the energy in the universe. Dark energy remains poorly understood, and its behavior at the edges of the universe hints at the existence of physical laws that we cannot yet comprehend. Physics provides us with an incredible understanding of the natural world, but these 5 places are where the physical laws as we know them break down. These phenomena push the boundaries of human knowledge and highlight the limitations of our current understanding. Until we develop a unified theory for everything, these places will remain mysterious, reminding us of the vast and unexplored frontiers of the universe. We hope you enjoyed our descent into the 5 places where physical laws cease to exist, and we invite you to our next episode,